So we'll be solving question for recent LeetCode contest. And the first question is count dominant indices. We're given an array of nums of length n. We need to find a index is dominant if its value is greater than average of all of its descendant value. And I need to count number of index which are dominant. So to solve this question, we need I is good if nums of I is greater than array of I plus 1 plus array of I plus 2 till array of n minus 1. So by brute force, if I pre-compute this, it will give TLE to me. So I need some method which will give me array of I plus array of I plus 1 up till array of n minus 1. If I get something like this, then I will divide this by number of elements and it will give me the answer if this index is good or not. So the new question come to us is how to compute array of I plus 1, array of I plus 2 up till array of n minus 1. So we know there is a technique called suffix array technique. Array technique in which we put the suffix of I is equal to array of I plus array of I plus 1 up till array of n minus 1. So for every index I will count suffix of I plus 1 because here I required a sum from I plus 1 and divide by number of elements. Yes, if this value turns out to be less than array of I, then this index is a dominant index. So let's see the code. I defined n, then suffix array, and I am going from right to left. Sum of array of n till array of n is just my array of n minus 1, right? So I'm defining suffix of n minus 1 is n minus 1. Then I am going to every element and I am saying next element sum plus my sum will do my new suffix sum. This is standard technique for suffix array calculation. And the count variable is for returning the number of count for which array index is dominant. So my first element is nums of I, and if I plus 1 is in range, like what if I is last index, so I put 0 because sum after them is 0. Then you take sum of I plus 1, else you take 0, and this is my length. So length would be something like this. Suppose I have 0 1 2 3 4 5. For this element there are 1 2 3 4 5 elements. Here there are 4 elements. Here there are 3 elements. Here there are 2 elements. Here 1 element, 0 element. N is 6. So we can do n minus I minus 1 would give me length of my suffix. So n minus I minus 1, and if this is last index, then it would be 0. Then no need because that would be not mathematically correct. And if my first is greater than the second value like this, then I will increase my count and return the count. So this is how you can solve the first question. Now let's move to the next question. Second question is merge and adjacent equal elements. You are given an array integer nums. You must repeatedly apply the following merge operation until no more merge can be made. If two adjacent elements are equal, choose the leftmost such adjacent pair in current array and replace them with single element equal to their sum. After each merge operation, array size decreases by 1. Repeat the process on the updated array until no more change can be made. Return the final array after all possible merge operation. So let's take this sample 3112. 3112. Here what is saying is, if these two elements are equal, then I can merge them into 2. So my new array will become 322. And I can again check if these two elements are equal, I can merge them into 1. So my array will be 3 4. Here these two are not equal, so they will not be merged. So output would be 3 4, and let's check this 3 4 only. For the second test case, 224. 224. These two are equal, I will merge them. These two are equal, I'll merge them. So I'll get 8. 8 is the sample. For the third one, 375. 375. Here no two adjacent elements are equal, so I will not be able to merge any of them. So I will return 375 as it is. Now let's make some observation to solve this question. Observation. We require two adjacent elements. So suppose I have element A, I have A as well. This would merge to become 2A, right? And if I have 2A before in my array, then they will merge to become 4A. And if I have 4A in my array, they will merge to become 8A. And if I have 8A in my array, they will merge to become 16A. So I got something like this. If I have A, and in the array of my answer, if I have A, then I can take this out and take this out, and I can merge it with 2A. And if before there was 2A, then I can merge this, will become 4A. And here if it was 4A, then I can merge this, it will become 8A. And here if I have 8A, I can merge this and it will become 16A. So I need a data structure in which I can take out the elements easily and check if it's equal to current or not. Suppose if I don't have a, suppose if I have A, 3A, again a comes, then I can check, okay, A and A are matching. This would be 2A and this would be 3A. They are not matching, right? So I will not do anything. I will append A in my data structure. Okay. So for my data structure, I need last element fast, and I need to append fast. So by thinking of these two property, which structure comes to your mind? It's stack. Stack comes to our mind by thinking this property. So what I will do is, I'll maintain a stack, and in this I will add elements, and I will check if the last element of stack is equal to current element. Then I will pop this element and merge it and add that to stack, and then again check it. But it would give me TLE because it would be O of n square solution. So to optimize this, what I can do is, to optimize this, suppose there are elements. This is merging correctly with me, and I will not stop here. I will check what I was doing earlier is I am merging it and then checking it again. So what if I check again until it matches? I will check if this and this match, okay, pop this out and merge this. If this and this match, pop this out and merge this. If they don't match, okay, I'll add this to my stack. So this is the core idea of the problem. This problem are generally called ad hoc problem, in which idea is if you get a chance to do the operation, you do it. This is the idea of ad hoc problems. You can search many good ad hoc problems on internet. You will find it. So based upon this observation, let's now jump into how to code this. So I'll maintain a stack and let's take the sample and then run it. If let's take this sample 3112. I mean my stack is empty. I'll put 3. I'll first check. Okay, if 3 is there in my stack, no, it's not there. So I'll put 3. 3 goes into the stack. Okay, now my pointer shifts to 1. I will check if 1 is there in the stack. No, it is not there. So I have to push it because there are no overlapping there. Now coming to this one, I'll check is 1 there. He will say yes, I am there. So I'll pop this and merge this to 2 and check if 2 is there in the stack or not. No, but it's 3. So I'll pop this and my new stack would become 3 and 2. And then I will check for this and this. I'll check, okay, these two are same. I'll merge this 3 and 4. And then I will check is 4 there in the stack. No, it's not there. So my new stack would become 3 and 4, and that is my output. So now let's go to implementation of this, how to code this. So here I made a stack. This is the stack, and then my current element, this you can change it as current. My current element, and I am doing a while loop while my stack is not empty and the last element of stack is equal to my current element. That thing I was saying to you here. If this is true, I'll remove the last element and add it to my current. And if this is not true, then I have to add current to it, and at last I'll return answer. And the constraints are 10 per 5, 10 per 5. So n is 10 per 5. So time complexity of this approach, you would think that okay, there is a for loop, there is a while loop, it would be n square, but no, there is a concept of amortized time complexity, in which uh, you analyze time complexity by how many times the array element are visited. So for this you would check something like this. uh, this while loop is going on stack elements, and this for loop is going on my current element. Each element can be present here or here. So each element at most 2 positions. can be there. So for n elements, I can 2n positions. So I am visiting each element 2n times. So my TC would be O of 2n, uh, which would be 2 times 10 power 5, which is less than 10 power 8. So it will give me accepted. This thing you can read it on various platforms like cpalgorithms.com. You will find a very good article on this amortized time complexity. So if this is not true, I add it, and at last I return my stack to the judge, and it solves the question. So let's move to the third question. Okay, it is a bit tricky question to me. Given nums and integer k, for any subarray L2R, define its cost as max of L2R minus min of L2R into R minus L plus 1. Integer n denoting number of subarray which cost is less than equal to k. So for a subarray, L2R, its cost is max of L2R minus min of L2R times R minus L plus 1. So I need to count, this is cost. I need to count how many subarray has this cost less than or equal to k, less than or equal to k. So the most naive approach is like go on all subarray, go on all subarray, and then calculate its max minus min into length. But you will see if I do this, time complexity would be O of n square to going on all subarray, and then O of 1 of maintaining max min and length, which is give me O of n square. But let's see the constraints in the question. Constraints are this. N is 10 power 5. So if I do O of n square, it would give me O of 10 power 5 square, which will give me 10 power 10, which will cost TLA to me. So it will not work. You need to think of something else. So first thing I thought was like, can I do some prefix and suffix calculation and optimization here, like maintain this as prefix max of L, prefix max of R, but it doesn't work. Then I thought of how to do this. Then I came with the idea. Let's make some observation. So my let's take an array of 1 2 3 4 5. Cost of this would be maximum of this minus min of this times length would be 4 into 5, which is 20. Okay. Let me add elements to it. So what elements I can add? Greater than max, correct? Like initially it was 1 2 3 4 5. I can add max से बड़ा, so it would be like I can add 6, let's say 1 2 3 4 5 6. And now if I take the cost, it would be max would be 6 minus min would be 1 times length would be 6 only, so it would be 5 into 6, which will give me 30. Initial cost was 24, so it's greater than 24. Okay, it's greater. And what next I can add? Less than min. Let's add minus 1. Then my cost would be 5 minus of minus 1 times 6, which would be 6 times 6, 36, which is also 24 greater. And third I can add is between. Can add is between. So if I add in between, then I will get, suppose let's add 3 again. 1 2 3 3 4 5. My cost would be max is 5, min is 1, and my length is what, 6. So it would be 4 times 6, which will be uh, 24. It is less than or equal to 24. Okay, so let's make an observation. I am on LR. If I adding an element R plus 1, my cost is always either remain same or it will increase. This is very important point to solve this question. So okay, now let's make a graph of cost. Either it remains same or it increases. So this type of function in mathematics are called uh, monotonic function. Monotonic function. And the best thing about them are the derivative is equal to 0. And if my function is monotonic, there is a theory which says if my function is monotonic, then I can apply binary search. Why this is true? Let me tell you. Suppose my function is this, okay? It is giving true, like same cost, है ना? Same cost or bigger cost, 34, 36, 16, 18, 20, and my initial cost was 24. So I can maintain like cost is either remaining same or it is increasing. It is never decreasing. So nature of the graph is not like this, like increase, decrease, decrease. For this graph, I cannot make binary search because suppose I am on this path. I found a value, but I don't know where to go now. The directions are not clear. Best answer can be here as well, but the beauty of monotonic functions are they tell you what is the best value. Like I can make a graph, suppose this. Huh. I am here. Okay, I am here. I want cost less than equal to k. And if my current cost of this r pointer is greater than k, then if I go forward, then cost will increase. So to decrease the cost, I need to go backward. Okay. If my cost is uh, less than k, like suppose my cost is here, L pointer, and I want to make cost greater than or equal to k, so I want to increase my cost. If I add this element, then it would be decreasing because the graph is decreasing towards this slope. You can see this slope decreasing nature. If I want to add, I need to go there. So in every path, I am getting a direction. So if I am getting a direction, I am on any path, I can decide whether to go left or to go right. And if this is true, I can apply binary search. Now the next point is how to apply binary search here to solve this particular question. So to solve this question, how to apply binary search is the main new point. So I will maintain for every I will find till when the cost is less than k. The last element whose cost is less than k, suppose is as j, and I will make this as like in this subarray it would be valid, right? So I will increase my answer with this subarray length j minus I plus 1. So I need to find where my cost is less than or equal to k. Okay, so for every index I'll find till where I can go at right at j index such that cost is less than equal to k for me. This is my new question to solve. So to solve this, we're using binary search. My left limit would be L equal to I, R equal to n minus 1, and I will be on a mid index. Mid would be what? Mid would be L plus R by 2. And if my cost of mid is less than equal to k, then this can be my j. This can be my j. So I'll maintain okay. Can be j. But I want greater j. So I'll go right. Else, okay, my cost is greater. I want less cost. So I'll go left. This is the template of binary search. Now the new question comes to us is how to find the cost of mid. This is the very tricky part. So for every index I, you need to find cost of I, and cost of I is uh, max of I and j. I and my mid, it would be good to say it is mid. I can undo it. Cost of I to mid minus minimum of I till mid times length would be j minus I plus 1. So the new question is how to find maximum of a range in I to mid. Like the new question comes to us is I will given I and j. I need to find uh, max of ij and Mean of ij. So this is a very standard question, and it will not strike you until you have not learned this topic. So this kind of topic is called range query, where you would be given a range, suppose L to R, and we need to find like max of L to R, mean of L to R, sum of L to R, many different queries for a given range. So to solve this question, I used there are 4 or 5 range query structure you can use. One is Fenwick tree, one is segment tree, and another is sparse table. So here I use sparse table to solve this question. So you can think like is a if you have not learned sparse table, you can think as a black box. As a black box, which would give me the query from L to R, and it gives me in O of 1. The it is give me O of 1. Their time is O of log n. You can read about them in internet. You will find many good articles on it. Even Eric made a video on this. You can search that how range queries work, and it is used in fourth and third question very much today's in LeetCode contest. So you need to learn it if you want to solve third and fourth question in all the contest. Okay, so whatever problem I had are solved. I tool J query solved. For every I last J solved. So my question is I think solved. So now come to the code and implementation of this question. So okay, so here I can just maximize it for you. N is my nums length, and this is the structure for my sparse table. You can search on internet, or you can keep a template of it. You will get it a template. I will explain how it works is like for every I, it calculates 2 की power I minus 1 and then fill value from this. It works on concept of binary lifting. You can search this on internet. You will find many articles regarding this. It is a bit advanced concept to be sure, but it is used in this question. There are many different approaches to solve this question, but I use this one. I think there are simple approach as well, but it didn't stuck my mind in the contest. So this would give me the range of any query L to R I can find. This ST max is from I till J. What is my maximum? ST min is from I to J. What is the minimum? And here is the computation of the sparse table. Okay. Now let's come to main code. Answer is 0. Okay. For every index I am finding the leftmost element for which cost is less than equal to k. So my L is I, my left search space. My right search space is n minus 1. And my best I is I minus 1. You can take anyone, you can take minus 1 as well. It will be good. And my current maximum means this range I till mid. What is the max of this range? And my current minimum, this range I till mid. What is my current minimum? And length of that range. I am doing binary search because it is more tonic. I am finding mid as L plus R minus L by 2 to avoid overflow. My length is J minus I plus 1, and here J is mid. So here I am calculating current max, means max of this range till I till mid. Current min is min of this range till I till mid. And my cost would be current max minus current min into length as it is shown here. Max minus min into length. Okay, if this cost is less than k, then I have found some j, but I am greedy. I want the farthest j, so I'll go on the right. So I'll go on the right. I'll go on the right. I'll go on the right. Else, I'll go on the left because I have found the k greater than equal to cost. And okay, and if the j I found out, if a j I found out was greater than I, means a valid subarray exists, and the length of this would be, like, you can keep it in mind, if subarray is from I till j, its length is j minus I plus 1. So here my j is best of j minus I plus 1, and at last I am returning answer. So this code is, as you can see, it is accepted and it is solved this question. It is a bit hard question. According to me, fourth one was easier than the third one. Don't know why they gave this question in the third problem. Now let's go to the fourth question. Fourth question, maximum score using exactly k pairs. I'm giving two integer array n1 and n2. I need to make exactly k pairs in which I1 j1 I2 j2 up till I k jk, such that the score is n1 of I into n2 of j, and I need to maximize the score, and the constraints given to us are 100 and 100. So to solve this question, first write the question what is saying to us. I am given array 1 of some elements. I am given array 2 of some elements. And I need to take elements from this or this. I need to make k pairs, and cost of one pair is n array 1 of I times array 2 of j. And you need summation of all. You need to maximize it. So first idea comes to our mind is greedy idea to solve this question. What is greedy idea? We'll pick the maximum pair. So let's take a sample. 132451. 132451. So here the maximum pair can be formed are like k is what? Let me check. K is 2. K is 2. So I'll pick 5 and 3, 15. And I'll pick second most would be like 4 and 2, 8. Give me what? But it is not true because index are not there. I need to pick 4 and 1. Give me 19 by greedy. But the optimal answer is 22. 22. So greedy fails here. Why? Because of concept of undo. Undo concept. I'll explain it. What is undo concept? Suppose I am on a grid. I have elements 1, 20, 2, 3. Let's take it as 4. Okay. 1000. Let's go 5, 2, 2. If I am greedy, I'll go from 1 to 20, then from 2, then 3, then 4. So it would give me cost of what? 4, 7, 9, 10, 30. But if I the optimal path will be 1, 2, 2, 5, 1000 and 9, which is much greater than my 30. So why GT fails? Because you go on a path, a maximum path, and there's a chance where you get all the values which are minimum. So you need to take this and move forward. But there was a possibility in which you took the minimum path and the value you got was very much bigger and you took it, and this is suppose B path, this is my A path, and my path sum of B is greater than path sum of A. So this is why greedy fails. So when greedy fails, what we do, we try all possible ways. How can I do this? Using recursion. I can apply recursion to solve this question. But time complexity of recursion would be something like 2 power n, because I generate all the subsequence 2 power n time 2 power n times, suppose O of k for matching, so which would be 2 power n plus m times k, and my n is 100. This would be much bigger than 10 power 8, so it will give me TLE. So I need to optimize this. So to optimize recursion, there is a concept of dynamic programming. Which is often called DP in short form. I'll use DP, in which what we do, we try to save states. We try to save states of earlier result to not calculate them again, and it will save time, of course it will, so let's think how to do recursion. So first thing which came to my mind was bit masking. I can make a mask of first array and then I can iterate, but bit masking takes 2 की power n time complexity, which would give me TLE. So I need a better approach to solve this question. But then I thought of, okay, this I is only bigger, J is only bigger. So I and J index are subsequence index. Subsequence index. So I can apply something like subsequence DP on it. Let's define my DP of I, comma J, comma remaining would be maximum product till 0 to I in array 1, 0 till J in array 2 with rem remaining operations. Okay, this is my DP definition. Now coming to transition. What is my DP transition? I have 3 options: skip I, skip J, and then make a pair. And max of all 3 would be my final answer. So let's see how I coded this. So, and one more thing, there's a common practice in which we initialize dp with -1, but here uh, one answer can be -1, so we have to initialize with a very big value, and it can be, in my case I took long min value. So I made dp of n plus 1, n2 plus 1, where this is array of length of size 1, first array, this is length of second array, n1 plus 1, n2 plus 1, and my k plus 1, and I initialize the dp with minimum value, and at last I am returning this function. Let's see what is this function. This function is I j remaining array 1, array 2, and my dp. So this is my up till ith index, up till jth index, like I said earlier, with remaining operation remaining, what is my maximum answer I can get. So if my operations is 0, like there are no remaining operation, I cannot do anything, so I'll return 0. And if any array parses, like if I is array 1 dot length, j is array 2 dot length, I'll return a very minimum value because I want maximum value. Okay, and this is the state of memoization. If dp of I, j, and ram is not equal to min value, then I will return it. If I have pre-computed this, then I will return it. And my answer is minimum value. My choice one is skipping the ith index. Skipping the ith index, the rest remains same. Choice 2 is skipping the jth index, rest remains same. And if my operations are remaining, then I will make a pair of this I and this j, and I will skip. I have taken this, right? I will go I plus 1, j plus 1, rem minus 1. Like, what is the maximum answer you can give me if I have I plus 1, j plus 1, and minus 1 operation? And my answer would be all those minimum, and I will store it, and it will give me answer. So it passes, as you can see, but what will be time complexity? So my dp states are like n length, n2, and k. So n1 times n2 times k. And for each dp states, I'm taking O of 1 operation into O of 1. So it would be n1 n2 into k. So here, let's take the max value of all those stuff. Here would be 100 times 100 times 100, which would be 10 power 6, which is in our constraint, so it will pass. This is the solution for this question.